Good afternoon. I'm Zilin, member of Team G05, consists of Aidan, Gironella, Jaura, and Qingyun. For the last 4 months, we were working on our capstone project called Low Footprint Lidar 3D Imaging under our client, Dr. Qamrul Huda. Let me give you a brief idea of our project goals before we go to more detailed explanation and demo. Currently available commercial solutions for industrial automation object and shape detections are frequently expensive and need large hardware and software investments. Usually, these solutions are not made for standalone and portable applications, where minimal weight, size, and power consumptions are required. So the goal of this project is to research and development and affordable solutions that lowers the entry barrier for small, medium-sized business and can be easily deployed in various industrial environments. And today we are going to present our project in 4 topics: hardware system, project demo, software system, and future consideration and conclusion. So here is all of our hardware components listed. Onion Tall Lidar 3D camera, Raspberry Pi 5, AI Head Plus, cooler, 128GB micro SD, power supply, and display units. This plot shows our 3D LiDAR cameras with the USB connections, so it will capture 3D depth data, measure the object distance, and provides the point cloud information for real-time processing. And next is the heart of our whole system. So it's a Raspberry Pi with a cooler and the AI Head Plus attached. So the Raspberry Pi is going to access the central processing unit, managing the LiDAR data acquisitions, and also the machine learning-based object detection and real-time data processing. The AI Head Plus is going to accelerate YOLO V8 models inference, so it's going to ensuring the real-time detection and classification while optimizing the power efficiency. So besides that, the micro HDMI port on the Raspberry Pi 5 provides you the capabilities of wide connection to the display unit. Let's move to the picture on the right. So it shows the back of the board with the 128GB micro SD card inserted. So it's going to store the system recordings and also the host the Raspberry Pi operating systems. And finally, here is our whole hardware system being assembled together with the power supply connected. The display units can use the HDMI cable for wired connection, or it can use the SSH or VNCs for wireless connections.
Now let's talk about the LiDAR image pre-processing and augmentation. On the left is the grayscale image we got from the LiDAR camera. As you can see that this is not very informative visually or to the model. Now you can see the same image on the right after we apply the color map jet transformation. What it does, it assigns heat map style color to the depth gradients, boosts the clarity, and enhance the spatial features of the image, and thus help us increase the detection accuracy of our model. Now let's talk about the model training. To increase the precision and the recall of our object detection yellow V8 model, we custom trained the model on hundreds of LiDAR images by manually annotating and labeling the image dataset. And in this slide, you can see the validation batch results of our custom trained model. As you can see in the different images here that the model successfully detects multiple classes such as like a person, hand, and also object shapes like rectangle as well. To measure the performance of our model, we used a normalized confusion matrix, where we saw a perfect recall of 100% for the hand and rectangle class, and a strong recall of 89% for a person class. These are pretty good results. However, the circle class remains underperforming due to the limited data, and we plan to address this problem in the future iterations. This is the precision recall curve that shows the per class average precision. Hand has a precision of 99.5%, person class has a precision of 87.7%, and the rectangle class has a precision of 82.8% with an overall 90% precision, which is excellent for a lightweight model on embedded hardware. And lastly, this is the F1 confidence curve, which shows the balance between the precision and recall across confidence thresholds. The model peaks at an optimal confidence threshold of 0.42 with a solid F1 score of 81%.
Let's now take a look at a live demo of our project. After running our Python script, we can access our WebSocket-based user interface by going to localhost in our browser. We see on the right the live data output of the Lidar camera with the object recognition results overlaid on top. We see that it is properly detecting my face as a person as well as my two hands. Underneath the output, we see a list of all currently detected objects, including labels and coordinates for both position and rotation relative to the camera. Moving to the left side of the screen, we have our recording controls. By default, the system is set to continuous recording mode with the bottom switch, and when I enable recording with the top switch, we see that a new file is made in our local file system. I can then stop recording by flipping the top switch again, and we can check that the footage was properly recorded and saved to our device. All recordings are stored locally, enabling the system to function as a completely standalone device. The file names indicate the recording mode used as well as including a timestamp. And we can look through the video here to see that the footage was properly recorded and saved. The second recording mode is trigger-based recording, where you can select an object to look out for, and the system will start recording upon detecting that object. I will select hand in this drop-down menu and then once again enable recording. We can see in our file system that a new file is not immediately created since a hand has not been detected. When I bring my hand into frame and the system detects it, a new triggered recording file is created, and it will continue to record for 5 seconds after the last detection of that object, then stop the video. After the system has not detected a hand for 5 seconds and it has finished the recording, we can check the video to see that it begins right when it first detects my hand, and continues for that preset amount of time after I lower my hand. These recording functionalities enable the system to be deployed in numerous environments and be tailored to different use cases. The continuous recording mode would be useful for industrial automation applications, whereas the trigger-based recording mode can be used for surveillance or just when you only need to record the important events. On top of saved recordings, the system also stores all object detection results into comma-separated value files for further inspection by the end user. These are also saved on the local file system in a file called detections.csv. This file is updated every time the system runs and detects a new object. These logs are useful for keeping track of events and can be exported for further analysis. We can see that just like on the UI, the system stores the timestamp, object label, object recognition confidence, coordinates in X, Y, and Z, which is distance, and angle of rotation relative to the camera. Just to demonstrate the functionality of our system one more time, let's try another triggered recording with a different object. We'll set the trigger object to rectangle and start recording. When I bring my phone into frame and the system correctly identifies it as a rectangle, a new file is created. It will continue to record and save this data as long as it sees a rectangle. We can see that the files are labeled with the object that was detected. We can see the hand and the rectangle, as well as timestamps so that we can easily distinguish between the different recordings. Again, we can see that the recording starts right when it detects that rectangle for the first time, and ends shortly after it stops seeing that object. This concludes the live demonstration of our system and how it can be used in various applications.
The future development will be focusing on enhancing the following functionalities. The first one is the portability. The current design is using a wall power supply. The future versions could integrate a high-capacity USB-C battery bank, such as the Anker PowerCore 10000 PD Redux. This would further reduce size, weight, and power, expanding the system's utility in mobile and outdoor applications. The second functionality we are going to improve is the flexibility of different machine learning model deployment. In the future versions, we can transition from the current YOLO V8S model to a more lightweight, prune, and quantized variant, improving inference speed and accuracy on the Raspberry Pi AI head. As more Lidar training data becomes available, the model can be retrained to enhance performance metrics such as precision and recall. This flexibility enables adaptation to various environments and task-specific needs. The third functionalities we are going to improve is the application programming interface, the API, for data access. To support future research and experiments, the system can include a well-documented modular API that exposes raw Lidar frames, proceed 3D data, and machine learning classification results. This would allow researchers to integrate custom detection models, logging tools, or visualization features without modifying the core system, promoting extensibility, faster integration, and easier debugging. The last functionalities we are going to improve is the latency, reducing the latency in real-time visualization. The current web interface has noticeable latency. In the future work, we should optimize the data flow between the Lidar sensor, inference engine, and the visualization layer. Potential improvements include multi-threaded buffering, frame skipping, and using a real-time rendering frameworks to reduce lag and improve user experience. In conclusion, we basically meet all the minimum cleanliness requirements. We successfully reduced the system constraint size, weight, power, and cost. We achieved real-time object recognition while maintaining low overall system costs, power consumption, and physical footprint. We visualized the result using a web UI and able to record footage on a low-footprint platform. We overcame the challenge of training YOLO V8S machine learning model. Thank you for your attending to our low-footprint Lidar 3D imaging capstone project presentation. We appreciate your time.